Ever wonder how electricity creates magnetic fields, or how we measure the hidden currents deep inside wires and coils? It feels like magic, but there is a powerful tool to unravel these mysteries. At its heart, determining the enclosed current using Ampere's law involves understanding a fundamental relationship between a magnetic field and the current that produces it. Ampere's law states that the line integral of the magnetic field B around any closed path is directly proportional to the total current passing through the surface enclosed by that path. This total current is what we call the enclosed current. The core mechanism of Ampere's law lies in Maxwell's equations, specifically relating static or steady currents to the magnetic fields they generate. Mathematically, it expresses that the circulation of the magnetic field vector around a closed loop is equal to the permeability of free space times the total current piercing that loop. The permeability of free space is a constant value, approximately for pi times 10 to the power of -7 Henry per meter. This law simplifies calculating magnetic fields for highly symmetric current distributions, where the magnetic field's magnitude is constant and parallel to the chosen path. To effectively determine the enclosed current using Ampere's law, you will follow a systematic approach. First, choose an imaginary closed path, often called an Amperian loop, that exploits the symmetry of your current distribution. Next, ensure you correctly identify the direction of the magnetic field relative to your chosen path. Then, evaluate the line integral of the magnetic field over this closed path, which often simplifies due to symmetry. Crucially, count all currents that pass through the surface bounded by your Amperian loop. Currents flowing in one direction are typically positive, while those flowing in the opposite direction are negative. Finally, equate this integral to the permeability constant multiplied by the sum of these enclosed currents to solve for the unknown current. This elegant law is a cornerstone of electromagnetism, offering a simplified way to analyze magnetic fields created by steady currents without resorting to more complex Bayet-Savart calculations in symmetric scenarios. An important insider detail is the right-hand rule, which helps determine the positive direction for the enclosed current relative to the direction of integration around the Amperian loop. Mastering the selection of the correct Amperian path is truly the key to unlocking the power of this law. By carefully applying Ampere's law, considering the path integral of the magnetic field, and meticulously accounting for all currents passing through the enclosed surface, you gain a deep understanding of how currents shape magnetic environments. This methodical approach not only helps determine the elusive enclosed current but also reinforces your grasp of the intricate dance between electricity and magnetism, paving the way for advanced electromagnetic applications.